Hello, this is question 11 from the 2022 Step 2 paper. So we're on to the probability and stats section, the last two questions. We got a batch of N USB sticks used on a network. Each stick has the same unknown probability P of being infected with a virus. Each stick is infected or not independently of the others. Right, network manager decides on an integer value of T. T goes from 0 up to N, but less than N. T is 0, no testing takes place, and the N sticks are used on the network. Yeah, great work from the network manager. Just plug them in and hope. But if T is greater than 0, the batch is subject to the following procedure. Each of T sticks chosen at random from the batch undergoes a test during which is destroyed. Wow. Okay. God knows what they're doing to them, but still. If any of these T sticks is infected, all the remaining N minus T sticks are destroyed. Okay. If none of the T sticks is infected, the remaining N minus T sticks are used on the network. Okay. If any stick is used on the network is infected, the network has to be disinfected at a cost of D pounds. D is greater than 0. If no stick used on a network is infected, you get £1 for each of the N minus T sticks. There's no cost of testing or destroying. Right, so let's just try and unpick some of this stuff. That's a lot of information. So we've started with N sticks, and they've all got a probability P of having a virus. Right, and then we're splitting that into T sticks and N minus T sticks. And then we'll test these. Did they say all of these get destroyed, didn't they? Yeah, all of these are destroyed. So these get destroyed. And then we will use these if none of T. So use if none of T infected. And then we destroy otherwise. Okay. So they've split them into those two blocks, two sets of sticks. Right, so that seems fine. And then we've got various costs or gains depending on the outcome, whether we've infected the network or not. Okay, so that's just to unravel the question. Right, so part 1, find an expression in terms of NT, D and Q, where Q is 1 minus P. Okay, for the expected net loss. Right, so yeah, so we're going to have then, we're going to have a gain based on, well, I suppose it depends if we've got any infection or not, doesn't it? We're using, right, so we're using N minus T sticks. So therefore, we've got the probability of, well, no infection is going to be, so yeah, P is the probability of infected, so Q is the probability of not being infected. So that is going to be Q to the N minus T. So that's our probability of having no infection. So therefore, expected gain, if we're actually plugging in, is going to be N minus T, more like an N minus T, because that's the number of sticks times the likelihood of actually not getting an infection, because that is our gain here, £1 for each one of those sticks. So that's what happens if we've got some kind of success here. But then the probability of infection then, so probability of infection is going to be 1 minus Q to the N minus T. And then we're going to get, so expected loss is going to be D times 1 minus Q to the N minus T. But again, that is if plugged in, because we've still got a chance of not actually using any of the sticks at all, as in we've got an infected stick in T. So if one of T is infected, then we don't plug in anything. Then no sticks used. Therefore, we've got the total expected loss then is, so we want, if we want an expected net loss, we're going to want to make that a, well, the loss will make positive. So let's say then that we've got the, I'm going to call the expected net loss ENL, just to go with that. So our ENL is the probability that we plug in anything at all. So that means we've got to have all of those T sticks that we tested have got to not be infected. So that's Q to the T. Then we've got our loss, which is D to the 1 minus Q to the N minus T. And then we have to take off the expected gain because we're trying to quantify the loss. So that would be N minus T times Q to the N minus T. Okay, so that is the, yeah, that's our expected net loss. That's fine. Quite a lot of variation, permutations that we got there. You know, first of all, you have to actually check to see if we are using any sticks at all, and then work out expected gain and expected loss. But yeah, not too bad. That's come out okay. So let's get a new sheet up and go on to part 2. Right, so let alpha equal all of that. Show that alpha is between 0 and 1. Okay, so, well, I might have to break this into a few bits. So we've got dt, n, t, and d again. So yeah, dt and n is all we've got on that. These are all positive things. D is greater than 0. T is greater than 0. N is greater than 0. So everything's greater than 0 here, especially as n is greater than t. So we can see that that is also positive. So I've got, okay, d is greater than 0, t is greater than 0, n is greater than 0, and n minus t plus d is greater than 0, as n is greater than t. Therefore, we've got that alpha has got to be greater than equal to 0. How's it going to be 0? Which one of these things? T is greater than 0. D is greater than 0. How are we making alpha equal to 0? And we're not, are we? Oh, if t is greater than 0. Right, I'm looking at the wrong one here. So t is greater than equal to 0. Right, okay. So that's fine. Now I need to show that alpha is less than 1. So I've got that well, let's have a closer look at the denominator then, I think. So we've got the denominator is n times n minus t plus nd. That's a useful thing to split out because we've got d times t. That's definitely going to be greater than, because we've got nd is greater than dt, and the n minus t is greater than 0, because n is greater than t. So that's dropped out okay. So therefore alpha is less than 1. Right, so that was fine. Show that for fixed values of n, d, and t, the greatest value of the expected net loss occurs when q satisfies the equation q to the n minus t equals alpha. Right, so we need the greatest value of the expected net loss. Right, so I need to find my expected net loss again, don't I? So what was my expected net loss? It was a horrible looking thing, which was on the previous screen. Yeah, I think I'll just pause things in order to copy all of this over, because that's quite a lot to actually copy across. So I don't want to be flicking between screens. Right, so that's the expected net loss that I worked out previously. So we need to differentiate this. So that's the expected net loss. So, and what we're changing? We're changing Q. We're fixing N, D, and T. So I want to do D expected net loss by DQ. So that is going to be, I mean, this is going to be better just doing this term by term, isn't it? I think. So I've got Q to the power of T times D. So that'll be T times D times Q to the T minus 1. Then I'm going to have, well, that's Q to the power of N. Actually, I'm going to get loads of Q to the power N's out of this. Yeah, I'm going to have Q to the N times minus D, and then minus N and plus T. So, okay, so I'm going to, what am I going to get on all of this? It's all Q to the N stuff. So plus N, Q to the N minus 1, and then I've got a, well, the T is the positive one, and then minus a D and minus an N. So yeah, that was handy that there were so many Q to the N's out of all of that. Okay, and I want to show that this, I'll think about whether it's a maximum or minimum in a minute doing the second derivative. Let's just get this value. So I want to make that equal to 0. So that equals 0 when, so I can flip the sign on this N, the N part of it. So let's get these on separate sides. So T, D, Q, T minus 1 is equal to N, Q, N minus 1, N plus D minus T. Okay. And what do I want to show that Q satisfies this. Q to the N minus T is alpha. All right, okay, so I've got the N minus T plus D bit. That's there. I've got the DT bit. Oh, and I've got the N, so it's all there. Oh, yeah, it's just all there. Right, okay. There's nothing else to do, really. So that means I'm just dividing through on both sides just to make it look like alpha. Yeah, it just drops out exactly as we want. So dt over n, let's get it in the order they've written it, n minus t plus d. So that is going to be q to the n minus 1 divided by q to the t minus 1. So that's q to the n minus t, which is equal to alpha. Okay, so that was fine. Now I need the second derivative. So let's go back to the red pen. D2 expected net loss by dq squared is going to be, right, so I'm going to now have t d t minus 1 q to t minus 2. God, this is a mess, isn't it? Plus n minus 1 q to the n minus 2 times t minus d minus n. Right, and I need to see whether that is going to be greater than or less than 0, and we want it to be less than 0. So how am I going to pull all of that together into anything nice? I mean, there's some similarities here and there between all of this. Is there? I feel as though if I can make these things look a bit more like each other, then I might end up, I don't know, let's get a minus in there as well. I'm thinking I can try and make things look like stuff off of alpha. So that dt, I could say that is going to be n minus t plus d times alpha times t minus 1 times q to the t minus 2. And then I'm subtracting to get the n minus 1, then n minus t plus d, q to the n minus 2. Right, yeah, I can see now this is going to be, so this is going to end up being negative, isn't it? Because we've got the same bracket there for n minus t plus d. We've got the same n. So I can say, right, this is negative, i.e. maximum, because we've got the alpha is less than 1. We've got the t minus 1 is less than n minus 1. And we've got that q to the t minus 2 is less than q to the n minus 2. So we've just got things that are all smaller in the first term compared to the second term. So overall, that has got to be negative, and we end up with a maximum. Okay, so that's another bit. Get another sheet up. Show further that this greatest value is this thing, where k is that. Okay, so the maximum, then we're just plugging back in to what we had before. Right, so I'm going to have to pause again and copy across what the expected net loss was, because again, can't remember what it is. Okay, so yeah, back again, copied that over, and what was I doing? So we have to, yeah, we've worked out when we're getting the maximum, and we need to show what the maximum actually is. So that's when we've got q to the n minus t is equal to alpha. So that's going to be q to the t 1 minus alpha times d, put in the extra bracket, and then n minus t times alpha. Okay, so we just need to get that into this sort of format. Got alpha to the k in there. Right, okay, let's figure out what that is and then go from there. So alpha to the k, this will guide me towards where I'm trying to go. So that is alpha to the t over n minus t, and that is equal to q to the n minus t to the t to the n minus t, which is q to the t. Okay, right, so that certainly helps. Go back to red again. So I need to get, what am I going to get with all of this? How am I going to get rid of any of these? I've got a 1 minus alpha d. I don't know really. Anyway, so en, that should be maximum enl. I've got there. So enl max is going to be equal to then alpha to the k, but now I want these alphas to be disappearing, which could be interesting. So I've got a d, a minus alpha d, a minus n alpha, and a plus t alpha. Okay, so how am I going to get all of that thing to disappear into anything? I mean, I suppose I can do something. I'm going to have to go back to this again, aren't I? I haven't really got any choice, I don't think. So that is, oh, but that is an n. Yeah, that is an n minus d. Okay, yeah, it is. This bracket again has appeared, hasn't it? So I've got alpha to the k d, and then minus. So if I've got alpha times that bracket, that's going to be dt over n. By the time I put all that in, so that is, well, that looks like it's it. If I take the d out, d times alpha to the power of k, then I'll have n minus t over n. Is that what I've got? Yes, it is. Excellent. So where k equals t over n minus t. Okay, right, so that dropped out all right as well. Right, happy days. Right, that was a big chunk of work, all of that. So part 3 then, the last part, for fixed values of n and d, show that there is some beta greater than 0, so that for all p is less than beta, the expression for the expected loss found in part 1 is an increasing function of t. Right, so let's read that again. So we got n and d we're fixing. So we've got a fixed number of sticks, we've got a fixed loss or fixed cost if we're disinfecting. Then there is some value of b that we want to keep the probability of infection below to show that we're actually increasing the expected loss every time we put another stick into the testing pool. Well, I mean, that kind of makes sense, doesn't it? Because if we've got a very low probability of infection, like really, really low, so say p is just hovering above 0, then we're better off just sticking all the sticks in, because we're getting £1 per stick. So the more sticks we can push through, the better. So that would make sense. If you've got very small p, then you're going to maximize profit by just using them all, which is the same as minimizing the loss, isn't it? So Right, so what am I actually trying to put on this then? So if we've got an increasing function of t for the expected loss, so that means as we're increasing t, then this thing has got to go up as we go up a value of t. I actually like this format of it, that without the alphas, admittedly. I mean, I've put these alphas in, but multiplying it out. So the thing that I used when I was doing, where is it, the differentiation. So this sort of multiplied out version is a much easier one to actually handle. So let's actually try that then. So what we're saying though is if it's an increasing function of t, if I write out the expected net loss for t and then write it out again for t plus 1, the t plus 1 is going to have to be larger. So let's get that better format up that I had before for the expected net loss. So that is qt times d, and then all of the other bits were qn's, weren't they? So I can have a minus, sure it was a minus because then it gives us the bracket that we want, because then we get a plus d, a plus n, and a minus t, so an n minus t plus d. So yeah, it just comes out like that, which is so much better than messing around with that sort of slightly ugly format up there. So now if I do this twice for t and t plus 1, then I need to show, so if increasing, let's make an assumption here, increasing function of t, then, so I'm going to make that statement and then show that it is the case. So put dqt minus q to the n minus t plus d, that needs to be less than putting a t plus 1 in there. So dq to the t plus 1 minus q to the n minus t plus 1 plus d. Okay, so loads of things are going to cancel here. I'm going to, in fact, all of this second bit on the left hand side is going to cancel. So all I'm going to have there is d to the qt. That'd be less than d to the qt plus 1, and then I've just got the 1. That 1 there is sat there, so minus q to the n. So that's what I've got. Actually, it's going to be a plus q to the n, isn't it? Because I've got two minus signs. Yeah, so plus q to the n. So is that necessarily going to be the case? How am I going to go about? Well, I don't really know. I'm trying to find, except there has to be, yeah, we're finding the condition under which this is the case. Yeah, so it's not always going to be the case. So let's try and get everything to the other side then. So I'll have a 0. Let's do a dq to the power t. Let's factorize that out of everything. So I'll have a qt. I'll have a minus 1. No, I won't have a qt. I'll just have a q. Yeah. Is that right? Yeah, so so that does dqt plus 1, and then a minus dqt, and then I've got this thing, so that's going to be plus, it's going to be over d, I'm going to have q to the n minus t over d. Right, and q minus 1 is minus p. So this is, okay, 0 less than d to the q to the power t, so that's minus p. So q to the n minus t over d minus p. Okay, so I need that. Right, so, okay, therefore, for increasing function of t, we need that q to the power of n minus t over d has to be greater than p. Right, which is what we wanted for p being less than beta. Right, so that's good. Deduce that for small enough values of p, testing no sticks minimizes the expected net loss. Right, well, yeah, I mean, I was saying that at the start of this question, that, yeah, if you've got, for really, really small p, you want to stick them all in to maximize your profit because you're getting £1 for each n minus t sticks. but that's not really following the game that they're playing here. They're wanting us to follow on off of the back of this. So what would we be saying then? So I'm going to try and squeeze it on here because I'm probably going to have to use some of this. Let's write it in the middle. So we got as P goes to 0, so that's small enough P. That means that Q is going to 1, and that means that Q to the n minus t will tend to 1. So we're getting that P needs to just be less than 1 over D. Yeah, so providing P is less than 1 over D, we have increasing function of T for providing, yeah, P is less than 1 over D, well, and small, we have an increasing function of T. So yeah, therefore you don't want to test any sticks. Therefore, test 0 sticks to maximize profit or minimize the expected net loss. It's probably better off to put it that way because that's what they've said in the question. Right, so yeah, that follows on quite nicely from what we've got there. Let's just check I've got a common, like a consistent thread through that last part, because there was quite a lot of if then that stuff going on. So if there's an increasing function of t, then we take our expected net loss, we put in t plus 1. If it's an increasing function, then putting in t plus 1 gives us a larger expected net loss, and I've shown that that happens at this point here. We need P to be less than, well, they've called it beta in the question, and it turns out to be Q to the power of n minus t over D. So provided P is less than that, we're fine. But if we've got really small P, or a small enough value for P, then that means that we're keeping P small, Q to the n minus t is close to 1. P just needs to be less than 1 over D, which is fine. And then we've got an increasing function of T regardless. Yes, that's probably the next bit I should put in. Increasing function of T for all values of T. That's what I should probably put in here, for all T. So it's not just some particular value of T where it then becomes an increasing function. It's just an increasing function of T right from the outset. As soon as you start including any sticks, you're increasing your expected net loss. So yeah, I think that's a nice addition there. It's just always pushing the expected net loss up, largely because you're pushing your profit down. You know, you're not increasing your likelihood very much of actually getting an infected network, but you're reducing the gain you're going to get because you're reducing your n minus t by increasing t. So your gain of £1 per stick is just dropping every time, and that's what's killing your loss. So, you know, you've still got more or less the same likelihood, very low likelihood of actually having a disinfect. So, but you're killing your profits. So, yeah, I really like that question. It had a nice range of stuff. You had a bit of probability stuff, you had a bit of algebra, you had a bit of calculus, a little bit of logic. It was a nice set all round, really. So that was a pleasing probability question.